Hello and welcome back, and thank you very much for watching this lecture video. We are talking about conjugated pi system, and remember this: in this molecule, we have carbon atoms that they are not octed, but in order to actually reach octet, they will be making double bonds with their neighbor. And in case of diene, we have two double bonds, and that means we have four p orbitals that they can make four molecular orbitals, and two out of those four they will be bonding, and the rest they will be anti-bonding. I showed you last lecture. I showed you actually how to get these orbitals, and I mentioned as we go up, as we increase level of energy or n, we will get more nodes, and that node is going to actually make the structure less stable. And in this case, the highest occupied orbital is number 2, that it has a node between carbon number 2 and carbon number 3. And here are the full diagram, four orbitals of the 1,3 diene. And as you see, first level, we don't have any node. All orbitals are involved in pi bonding. Second one, we do have a node, one node here. That means between carbon number 2 and 3, there will be no bond, no pi bond. And then like the pi bond, there will be between first, second, and third, and fourth one. Now look to the number 3. Number 3 is telling us that the only place to have a double bond is between carbon number 2 and 3. And that means it's possible to get the double bond between them, but that's going to cost us energy. Let's prove it. And imagine you have such a structure. We said we can run some resonance, and if we do it, that's going to leave us with a positive charge on this carbon, and then there will be a double bond here and a negative charge on terminal carbon. So I got suspicious that it has a double bond in the middle between carbon number 2 and carbon number 3, but the side effect of it is having two charges. Well, the starting compound, it has a zero charge compared to the one on the right with two charges. So I'm going to say this one will be more stable. Yes, does not have a double bond between carbon number 2 and 3, but the charge is 0, and any atom that you pick is octet. And now when you look the bond length between carbon number 2 and carbon number 3, beside hybridization, now you will understand why the bond length here is shorter than a single bond. Okay, the reason behind it, we said it. Okay, the reason behind it, that we can have sometimes we can have, forgive me, sometimes we can have double bond between the carbon number 2 and 3, and that's gonna shorter the bond. And it's not like it absolutely is not gonna happen. It can happen, but maybe like not all the time. Okay, so I said the highest occupied orbital, it has a lone pair between carbon number 2 and carbon number 3, and that's gonna leave you with technically this structure. You draw the double bond between carbon number 1 and 2 and 3 and 4. And while the first structure, it has all the atoms are involved in double bond. And the question is, what will happen if I add another pi bond to the system? This time we're going to use 6p orbital, and we want to see what will happen. And of course, I'm going to get 6 molecular orbital, and out of those 6 to 3, they will be bonding, and 3 they will be anti-bonding. Okay, now. So I have 6 p orbitals. That means I have 6 electrons, and because I have 6 electrons, I can occupy 3 of the atomic orbitals. 3 of the bonding orbitals. So as you see here, those 3 orbitals, the lowest 3 orbitals got full. And now let's zoom on the highest occupied orbital. The highest occupied molecular orbital is number 3, and the lowest unoccupied molecular orbital, it will be number 4. Number 3, it has two nodes. Okay, and because it has 2 nodes, if you look to the like the both tails, like or both terminal side of the the molecule, they have the same faces. Like both of them are red. If I go back, this one. Let me show you the full diagram. And here we have this one blue or in purple, any color that you see, and that one is red. Okay. That's going to affect the stereochemistry of the reactant a lot, and it will technically enter completely different product, and you will see it by end of this actual chapter. Now, normally number 3 it will be the HOMO orbital, and 4 it will be the LOMO. But if I give it energy, I can take one electron and send it to a higher orbital. Now, the highest occupied orbital, it will be number 4, and the lowest unoccupied orbital, it will be number 5. So by giving energy to the system, we can change position of the HOMO and LOMO, and that's going to affect reactivity of the actual starting compound. And later you will see that why we get unique product whenever we get, for example, whenever we give energy to such a system. Let's practice some basic chemical reaction for dienes, and slowly we're going to move to, for example, we're going to move to reactions between dienes and also their stereochemistry. Okay, I have a double bond and I'm adding hydrobromic acid to it, and in this case I'm going to say this. I have an alkene and I'm adding bromic acid to it, and I have a terminal and carbon, and that one it has 2 hydrogen. Now, based on Markov-Nikov rules, we said whenever we are adding H to the system, to the double bond, we will try to make it to generate the most stable carbocation. The most stable carbocation, in this case, it will be tertiary. And because it's a tertiary, it will be really stable. The reaction is going to go through technically SN1 mechanism, and it will give us the final product with the bromide sitting on the tertiary carbon, while hydrogen is sitting on the terminal carbon. Now, what will happen if I add this 1 mole of hydrobromic acid to the diene? Okay, and let's write here. Let's write it as this graph. And as you see, we have a double bond. A double bond, it can go after bromide, after hydrogen. It will take hydrogen from the system, and sorry, from HBr. It will leave us with a positive charge on carbon number 2, plus bromide hanging around there with a negative charge. Okay, so I got a carbocation that is allylic. Okay, be careful. This one is allylic. What do I mean by allylic? It's neighbor to a double bond, and that's the reason this carbocation is going to be stable, because it's allylic. Okay, and how about the second pathway? The second pathway, we're going to go after H. We will take this H, we will attach it to carbon number 1, and again it will leave us with a positive charge on carbon number 2. So we got the same intermediate. The first intermediate, it will be the same for both of them. Now, the top mechanism, I can top pathway, I can add the bromide or the nucleophile to intermediate, and that's going to leave me. That's going to technically put the bromide on the carbon number 2, while hydrogen is going to be on carbon number 1. And I do have a double bond between 3 and 4 that is untouched, and I leave it as it is. Okay. Well, the second pathway, instead of adding the nucleophile, our intermediate, it can do rearrangement. Remember, it's allylic, and because it's allylic, it can do this. Move those 2 electrons between carbon number 2 and 3, and it's going to give us hydrogen on carbon number 1, double bond between 2 and 3, and a positive charge on carbon number 4. Okay, now I have a charge on carbon number 4, and the next step, I'm going to add the bromide to it, or our nucleophile. The bromide, it will go after carbon number 4, and now I will have bromide sitting there while hydrogen is here. So what did I get? On the first one, I got hydrogen on carbon number 1 and bromide on carbon number 2. I'm going to call it 1 and 2 adduct. And this one, 1 and 4 adduct. So it's showing us technically where we put these 2 species. I'm talking about hydrogen and bromide. Okay. Now, again, I said the first step, you will get same intermediate, and intermediate because it's the same. So activation energy for them, it will be the same. But the second step here, our intermediate did not go through any rearrangement. We got an activation energy number 2, and this one did some rearrangement. Maybe the rearrangement is not going to cost us a lot. You can call it EA2 prime, and this one is going to be really, really small. But the main one, it will be number 3. Okay. Even if you say we will not detect this at all, I'm going to say you will see this. Okay. So let's assume we're not going to really see this one, and that's going to be activation energy for the second step. Okay. Keep this one in your mind, and I'm going to go after them. I'm going to go after them again in a minute. Okay. So I got 2 products. In the 2 products, the difference between them, position of hydrogen and bromide. If I repeat this one with bromide instead of hydrobromic acid, I can get, again, the same thing. I can get 1 and 2 adduct, or 1 and 4, or and then adduct. And it's going to be exactly the same story as HBr. And okay. Now, I said it depends what's the temperature of the reaction. The product that you will get, the ratio, it will be different. Okay, and this is here. If you increase the temperature, one of the product it will be favored, and as you see, the 1 and 4 it will be favored over 1 and 2. Okay, let's go after those and understand why we get different ratio between them. 1 and 2, we say 1 and 2, we say they are kinetically favored. Okay, and then so kinetic is favoring 1 and 2. What does it mean? It means it's faster. Okay, it's faster. That one you will get it faster. But thermodynamic is favoring. Thermodynamic is favoring actually 1 and 4. So again, let's say kinetic is favoring 1 and 2, while thermodynamic is favoring 1 and 4. Okay, and I told you the first activation energy for both of them it will be the same, but the second activation energy for 1 and 2 is smaller than activation energy for 1 and 4. So I'm going to say the activation energy for 1 and 4 is bigger than 1 and 2. So this one is 1 and 4, while that one is 1 and 2. And because the 1 and 2 it has smaller activation energy, it will be faster. You will get more from it if the temperature is low. Now, what will happen if I increase the temperature? If the temperature is big enough, then the gap between them is not going to really affect ratio of the product. And in that case, I'm going to say like the molecule has enough energy to pass any activation energy that you put in front of it, whether it's this one or let's say that one. Okay. Now, what will happen if you raise the temperature? If you raise the temperature, it says 1 and 4, it will be favored. And what's the reason behind it? The reason behind it, 1 and 2, you will get a double bond that is terminal. But 1 and 4, you get a double bond that it has 2 substituents at least. And that one is more favored or more like a stable because we will get more donation from the methyl groups. And we called it Zaitsev product in organic 1. And well, the first one we call it Hoffman, and we said Hoffman product because they have hydrogen instead of, let's say, carbon substituent, they will be less stable. Okay, what was the reason behind of getting 1 and 2 faster than 1 and 4? The reason behind it, when you add hydrogen, you will get a carbocation. You need to ask yourself, where is the bromide? Bromide is not just like simply flying or hanging somewhere else. No, it's going to be close to wherever we have a positive charge because there is electrostatic charge between them. So bromide is hanging around second carbon, and if bromide, the second bromide technically start to see the carbocation, it will catch it and to neutralize it. But in order to find carbon number 4, it has to wait because it's way far from it. And that's the reason we say we get this one faster. Okay, kinetic is favoring the 1 and 2, while the thermodynamic is favoring the 1 and 4. Okay, and next lecture I'm gonna practice some chemical reaction that they are involved. Homo and LOMO of diene and triene compounds, and you will see like how number of nodes will affect the stereochemistry of the product. But for now, thank you very much and appreciate for watching this lecture video.